Welcome to Lesson 11C, Local Ventilation Introduction. We're going to introduce local ventilation and talk about hoods, suction velocities, and something called isopleths. Introduction, we talked about general ventilation, and this was for rooms and buildings. And we also talked about ventilation in tunnels. Local ventilation is basically hoods, devices that capture and remove contaminated air, either particles or vapors. For example, in a kitchen, cooking on a stove, you have a range hood above it. You have some kind of a source here, S. Typically you have a fan or a blower that draws air out of the room, so there's some Q going through the hood. The main idea or the purpose of these hoods is to draw contaminant away from the people and out of the room. So the difference between general ventilation and this, what we call local ventilation, is that for local ventilation with hoods, our goal is to do not let the contaminant get into the room in the first place. With general ventilation, we had a room and we used the ventilation system, cleaners and stuff like that, to get rid of the source. Now we're saying let's try to get rid of that source before it even enters the room. We will consider both vapors and particles. We'll have two different techniques of how to remove particles and how to remove vapors. Let A face and U face be the area and average speed at the hood face, the actual open part, the inlet of the hood. So if I quickly resketch the hood, this part that is open, and there's usually a screen perhaps or something, but we still count that as the open area. This would be A face, and then the average speed would be U face. Of course, there's a flow rate Q coming out. So the face is just what these HVAC people call the inlet. We can write a simple formula, U face, the face velocity. We say velocity, but it's really a speed because it has no direction. It's the average face velocity, and the equation would be U face is equal to Q over A face. Now let me give you a little fluid mechanics lesson here. There's a fundamental problem with designing hoods, and I like to call this the candle effect. You take a candle, if you blow, you generate a jet and you can easily blow out that candle. However, if you try to suck out the candle and you think that you're going to create some kind of flow this way, it won't happen. What actually happens is that you get suction from all directions and the speed near the candle flame is extremely small. And so you cannot suck out a candle.
Hey Luke, I bet you $1 you can't suck out a candle. All right, give it a try. Thanks, Luke. So why can't you suck out a candle? You can certainly blow out a candle pretty easily. So when you blow, you impart momentum to the air and it goes straight out. And so the candle could be, anywhere here and you'll still blow it out. But when you suck, you're sucking air from all over, and even from the back of my head, that air is coming all into that opening. And so even when you have the candle real close, you don't get much velocity. I was able to suck out the flame one time, but look what happened to my lips. So that's why you can blow out a candle, but you can't suck out a candle.
Let's also define isopleths. Isopleths are simply contours or curves of constant speed, not velocity, because we don't care what the direction is, just the speed of the air. For example, let's consider a 10:1 aspect ratio rectangular inlet. This is a face, and we'll typically put on a coordinate system that is centered at the inlet. That green shaded area is the inlet, so X will be that direction, Y will be vertical, and Z will be to the side there like that. The suction slot height would be S. We have a symmetry plane here. In the middle, we can have another symmetry plane here. We can plot contours of constant speed, which we call isopleths, for this inlet, this suction device or hood. And what I want to emphasize is that the speed decays extremely rapidly away from the face.
This book has about a 10-to-1 aspect ratio. So if we pretend that this white portion here is a slot, that's a suction, and I put a probe right in the center line and approximately one slot from the inlet, pretend this is the inlet, about here, the speed is only about 22% of the average face speed through that slot. So you see that it decays very rapidly. If you go out 2 slot distances away, right in the middle, it's about 10%. So it really decays rapidly.
I have these isopleths plotted for this rectangular aspect ratio 10 inlet that we're talking about. The horizontal axis here is x over s. And so when you're at x over s equal 1, this is s. We're one of those distances away from the center line, so we're right there. The isopleths are these curves. The vertical axis is y over s, so that's this dimension. So here you can see when y over s is a half, you're half of an s away, a half a slot height because everything's symmetric. We're only showing half. This is the symmetry plane. So the actual inlet goes down like that as well. What are the values right here at x over s equal 1? These are in percentage, so it's between 20 and 30%. This is the 20% isopleth. This is the 30% isopleth. And so between those, if we do a little interpolation by eyeball, we can say that at x over s equal 1 and at y over s equal 0, right on the center line, in other words, u over u face is approximately 22%, which is really small. When you get to 2, it's about 10.5% here. You can see the rapid drop off. It's 100% right at the inlet face, and then it rapidly drops as you move out. By one slot height away, you're down to 22% of the face. That's a side view. This is a top view. It's 5S because, again, we're doing half. So this is the symmetry plane through the middle, looking from the top. So this is a top view, and this is the side view. And we see those same kind of isopleths. Here's your 20%, here's your 30%. When we're right in the middle at 1, that's our 22% that we had up here. So that agrees. And it's fairly constant until you get near the corners. For example, we come 45 degrees out. That distance is s over 2. We're at the 15% isopleth. In other words, at this location, u over u face is only about 15%. In some of the homework or quizzes, if I give you a rectangular slot and I give you some x over s, you'd find that on this horizontal axis, say it's 1.6, and then I give you some y over s, and you come up, maybe it's around 0.8, so you see those intersect at roughly this isopleth, which is 10%. That would be your u over u face that you would use in your analysis. So those are for rectangular geometries. What about round geometries? A round inlet, basically just a pipe. Again, I'll shade that as a face, diameter d. There's some q, but the air comes in from all directions, even from the back. Again, the velocity decays quite rapidly as you go away from that inlet. We'll call this x, and then the only other dimension we need is r, the radius. This is axisymmetric. It turns out that this is why you can't suck out a candle, because you're drawing air from all over the place. If I take a round inlet, let's suppose this is a suction device, and this is the face. The face velocity is the average speed through that inlet. And if I put a probe about 1 diameter, this is a diameter, so about 1 diameter away, right at the center line, the speed there is about 7% of what it is at the face. And it decays very rapidly as you go back. This is called unflanged. You can add a flange to it right at the entrance, at the inlet face. And that flange will help because it forces the air to flow straight along the flange, parallel to the face, and then get sucked in. You'll still get a little bit of flow from the back and over, but it'll be a very small velocity. So that helps a little. This is called a flanged inlet. Now if I add a flange at the inlet, so this is a round inlet with a flange, it directs the flow a little bit more parallel to the face. Flow isn't coming from the back. Now that helps a little bit. If I put my probe 1 diameter away at the center line, we now have about 10% of the face velocity. Improvement a little bit from without the flange, it was around 7%. This brings it to 10%. So it helps, but not a whole lot. So I want to show you the isopleths first for an unflanged or a plain circular inlet. This would be 20%, 10%. Now this plot is a little bit tricky because there's no horizontal axis on that top view there. Well, it's actually side or top or anything because it's round. This is from the ASHRAE handbook. They're also plotting the center line value, and there's actually an equation for it. So this equation is nice, but it's on the center line only. Use that equation. That's easier than trying to pick numbers off the plot, but that's only valid on the center line. In other words, R is equal to 0. We're plotting X over D here. The same axis applies to this upper plot. If I could duplicate that, X over D 1.0 would be there. You have to kind of draw a line up to see where you are. These are the isopleth values, the 20%. For example, at X over D equal 1.0 and R over D equals 0, in other words, on the center line. So we're just coming straight out to 1 if this is 1 diameter, about that distance. So we're right there. What is the speed compared to the face speed, U face? We can either use the diagram or we can use the equation. If I use the diagram, I would say that I'm right at this point where we have 1.0, and I've gone up to 1.0 there. So it's this point right here where we're reading off the plot. It's pretty much exactly between 5 and 10%. So I would call that 7.5%. So for our example, from the plot, U over U face is 7.5%. From the equation, and we can use this equation since we're on the center line, we have U over U face equal 1 plus 40 over pi, and then X over D is 1. You get 0.0728 or approximately 7.3%. It's very difficult to read off a plot, so I would say those agree to the accuracy of the plot, but this one is more accurate. Now, if I had, for example, at X over D equal 1.0 and R over D equal 0.6, at that point, approximately there, this is the 5% isopleth. And so U over U face is approximately 0.05 or 5%. So that's another example. I also have isopleths for the flange, and you can do the same kind of calculations. We don't have a centerline plot, but we do have an equation at X over D equal 1.0. We're between 7.5 and 10%, these two, roughly halfway in between, so I just took the average of those, and we'd say that U over U face is approximately 8.8%. If you're right on the center line, we give these equations that we got from the ASHRAE book. There's two different equations. This one's pretty good, but this one doesn't work very well. We'll try it at X over D equal 1. Well, X over D equal 1 here to any power there just gives you 1. So U over U face equal 10, and that does not agree with what we get off the plot. So even though this is in the book, I don't trust this equation. I trust the plot better. It turns out that this equation works. I'll do an example at X over D equal 0.5 and R over D equals 0. So we're on the center line. So U over U face is equal to 1.10 times 0.070 to the X over D, which is 0.5, and you get 0.291 or approximately 29%. That agrees pretty well with the plot. On the center line, you would be right here when X over D is 0.5, and that's the 30% isopleth. Not perfect, but this equation is pretty good. Let's do a more realistic example. Some of the new kitchens, they have these fancy looking hoods, and some of them are actually round. So I took the specifications off the website. It's just a round pipe basically, but nice and shiny, and it has all these lights and stuff on it. But the face diameter is 14 inches, and the airflow, they say it has a range from 150 to 940 CFM. Let's estimate the airspeed at a location 2 feet from the hood face along the center line when the hood is operating at 500 CFM. If this is the face here, that's the area A face, we're going to go down 2 diameters. So we're going to be down near our pots and pans here, so around this point where you're trying to suck up something from your stove. This guy's giving off some chemicals or some steam, and you want to take that up into your hood. Is it going to work? Let's do the case when the hood's operating at 500 CFM. So let's just use the equation since it's on the center line. In our case, it's a round hood without a flange, so we use this equation on the center line. This will give us 1 plus 40 over pi times 24 inches over 14 inches squared and negative 1. This turns out to be 0.02603, or about 2.6%. So you notice how rapidly the speed decays as you move away from the hood inlet. This is U over U face. And we also know that Q is equal to U face times A face. And so from that we can solve for U face, which is equal to Q over A face is equal to 4Q over pi d squared, since A face is equal to pi d squared over 4 for a round inlet. And so we can solve this for U face. 4 times our given CFM of the hood, the Q, pi d, 1 foot is 12 inches. And then this whole thing squared, you get 467.7 feet per minute. That's the face velocity. And so here at our location, U equal 0.02603 times U face, and U face is this value here. So we plug that in and we get 12.2 feet per minute. That's 0.062 meters per second, which is very slow indeed. You can hardly feel that at all. So that's why hood design is difficult, and that's an understatement. The reason being the candle effect, which we talked about and I showed you. If you're cooking like this, and especially if you're off center and you have smoke coming up, it's very easy to get this smoke to not get sucked into the hood. If this hood is not wide enough compared to your stove, I don't think it's going to work very well. You've all experienced this working in the kitchen. You just can't suck the stuff out that you want to suck out from your stove.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3. That's all there is to it.